It's the physics video lecture, Physics 203 video lecture 14. We're talking about Hamiltonian mechanics now. Great subject. And I had a question about converting a Lagrangian to a Hamiltonian. So since that's exactly the topic we're on, let's go ahead and start with that. So we want to get the Hamiltonian of a point mass in, not Cartesian coordinates, of a point mass in cylindrical coordinates. Okay, of a point mass in cylindrical coordinates. And so I can take all of the steps here, and then at the end of it, I'll refer to what we ended the last lecture with about that general formula. Good. So the first step when we're doing this is we have to find the right coordinates for our mechanical system, and we've decided that they were cylindrical coordinates. So we have to start with the Lagrangian. And I'm just going to write this down and say a few words. So first let's just write it down. Rho dot squared, rho squared, phi dot squared plus z dot squared. And then it would be minus u of rho, phi, and z. So here I actually cut to the chase, didn't I? I've noticed people sometimes think they have to start all the way back at Cartesian coordinates to get their cylindrical coordinates, but actually the cylindrical coordinates have this part of the kinetic energy, which we've inherited from the plane polar coordinates. Really, cylindrical coordinates are plane polar coordinates with the z-axis. So let's go ahead and draw this. Okay. So we start with x, y, and z. And if we were just in the xy plane, we could just have plane polar coordinates, which are convenient. But now we're in free space, and so there is a vector r, and one way to express that vector is it's going to be rho hat plus z. Now this part right here, okay, that's just a projection down on the xy plane. This would be the plane polar coordinate part, and I've just renamed it. Okay, so instead of using r, the letter r, I'm using rho for the distance out from the z-axis, and then my z hat, I guess I got to do that, or maybe I could call it k hat. Okay, it'd be the z coordinate in the k hat direction. So these would be my plane polar coordinates, and for plane polar coordinates, using the letter r, we would have just taken these right there. That's what we did our central force problem with. Okay, and the z and the k hat is clearly perpendicular to the rho hat. So you would say you go out here, rho, and rho hat is the unit vector, just as before r hat was. So yeah, you don't have to go back to your sines and cosines to generate this expression. You inherit it, and now you just add the z dot squared for the z hat direction. Good, so I'll put here from plane polar coordinates. Good, and there's our Lagrangian. What comes next? We have P sub rho is equal to dl d rho dot, and that is m rho dot. We have P sub phi is equal to dl d phi dot, that is m rho squared phi dot, and P sub z dl dz dot equals mz dot. Okay, so we'll make use of those. The Hamiltonian starts out just as the energy. I'm already going to call it H. And in the simplest case like this, well, I'll put its definition. It's dl d q sub I dot minus L. In this case, I equals 1 to 3. You're just going through rho, phi, and z. In this case, it's actually just T plus U, as we demonstrated in the past. So we'll just rewrite this rho dot squared plus 1/2 m rho squared p dot squared 1/2 m z dot squared minus, not minus, plus u of rho p and z. Okay, not yet the Hamiltonian, because now we have to make those substitutions. Maybe we have to get rid of the rows, phi dots, so rho dot, phi dot, and z dot, and replace it in terms of p. Now, in this simple case, they're not mixed, right? P sub rho only depends on rho dot, P sub phi only depends on phi dot, P sub z only depends on z dot. Therefore, these are more or less trivial to do, but we have to make that substitution. And we're going to get P sub rho squared over 2m plus P sub phi squared 2m rho squared, right? We make that substitution, phi dot divide squared, cancel one of the m's, and plus P sub z squared divided by 2m. Plus u, rho, v, z. Okay. Now we actually have the Hamiltonian. If we had to, we could take Hamilton's equations of motion, and we plug one into the other, and we get the Euler-Lagrange equations back again. So we're not going to go there. So we don't have to do that. So this is how you get that Hamiltonian. Now let me add an assignment. I don't think I had it up there last time. There's one more really important Hamiltonian that we want to get. Homework. Construct, find H of, I'll say that next. Find H, the Hamiltonian for the Lagrangian that we had worked with before, the electromagnetic one, 1/2 m x dot squared plus y dot squared plus z dot squared minus q phi plus q a dot v. Okay. So we looked at this thing. It's right here. We worked with this last time to show that the Euler-Lagrange equations gave us the proper equations for a particle in an electromagnetic field. This time we're going to do something different. We're going to just get this Hamiltonian. I want to say a couple things about this. So here we have phi, not q, we have phi is equal to phi of x and y and z. A is the vector potential, each component, right? It has three components, ax, ay, az. Each of these depends on x, y, and z. We could make these both time dependent, we're not going to. Okay. And the vector v is the vector x dot, y dot, z dot. So this here is v squared. if you want. We're going to do this in Cartesian coordinates. That's b squared, that's the vector b, that's how that's put together. And this is a really important Hamiltonian. It's the one that's used in quantum mechanics for atomic physics problems. Okay. So you want to see where that comes from. Go ahead and erase this. Because typically the first time you see that in atomic physics, you don't know where it comes from because you haven't studied Hamiltonian mechanics yet. So yeah, we definitely want to get that one. Continue on down here like that. And we're using this recipe here. You notice you can't just say t plus u right here because this thing is not of that standard form, okay? But it's, we saw before, it's a legitimate part. So you're going to go to this recipe and carefully write it out, and then you're going to make your substitutions. What you're going to find, I'm even going to get started on this with you. So we have, I'll do a little work here with you. So we will have p sub x is equal to d L dx dot, right? So there's easy. We have mx dot. But don't forget what we have here. We have a q a sub x dot dotted into x dot. Okay, a sub x times x dot. So that derivative is q a sub x. You get the same thing for y and z. So x dot is equal to p sub x minus qa divided by m. And this is what you're going to do in the similar substitution to what we did up there. When you square it, you're squaring this, and I just want to tell you, you don't have to go beyond this expression. You don't have to square this out and have the cross terms and stuff. Leave it in this form. You're going to have a y and a z, and it takes on a very clean vector form that way when all is said and done. So don't square this expression. Just leave it the way it is and look at it. Okay. So yeah, this Hamiltonian is important. It goes into all the atomic physics problems where you're coupling to an electromagnetic field. So you've probably seen it before, or quite possibly you've seen it before and didn't really know where it came from. Right? They just serve it up to you. This time we actually see where it came from. So that's an important problem. Good. And yeah, now I'll say something about the general formula we had last time. So last time we had ended with we had L was equal to 1/2 Q dot dotted into, we didn't use the letter A, we had T, Q, right, that was our quadratic form, plus A of Q, Q dot, minus L naught of Q, and T, I believe. And the thing is, this is one of that form. This expression was more general because we didn't necessarily have a diagonal matrix T right here. In this case, that matrix is diagonal, and that's why the substitution is no problem. And then look back in your notes what we had there for H. It really was this process here with slightly different letters. So actually, yeah, H equals, etc. That's in your notes. What I just want to say is, here, T, I, J of Q is not necessarily diagonal. It can be. And in that case, you had to get the inverse matrix, okay? Here, we're just doing 1 divided by for our inverse. Okay, good. So we'll leave it at that. Let's see what's next on our plate. Okay, so the next thing is to talk a bit about the advantages or some other properties of the Hamiltonian method. I'm going to erase all this. So we have, from a Lagrangian to a Hamiltonian. And then, of course, we have the canonical equations. So the topic I want to discuss is cyclic coordinates. In the Hamiltonian method. So we know how this works with cyclic coordinates in Lagrangian mechanics, and we know that if we have a cyclic coordinate, we have a conserved quantity. And the same thing is going to happen in Hamiltonian mechanics. So suppose we have, suppose H equals H of Q2 to Qn, piece of 1, piece of 2, all the way to piece of n and p. So we constructed a Hamiltonian with n minus 1 and n, so n momenta, so n coordinates and momenta, but one of the coordinates is cyclic, and I've just let it be the first one. Okay, so I don't have to put the kth one in anywhere. Same thing holds for any Hamiltonian, you just relabel them. Okay, so suppose it's missing the here q sub 1 cyclic. So what are the canonical equations? We have d h, or let's write it this way. We have q sub I dot is equal to dh p sub I and p sub I dot minus dh dq sub I. Okay, minus sign comes is the one where you just have, this is actually Newton's law right here in the basic case. Gets the minus sign. Yeah. So those are the canonical equations. I equals 1 to n, but q sub 1 just happens to be cyclic. Make sure we indicate this is the 1. Q sub 1 is cyclic. So over here, p sub 1, draw my arrow over here. dh dq sub 1 is trivially 0. P sub 1 dot equals 0. Therefore, p sub 1 is constant. Okay, so that's the same as before. You have a cyclic coordinate. If q sub k is cyclic, then p sub k is conserved. Okay. So that's the same as in Lagrangian mechanics, but we have an added advantage in the Hamiltonian method. do is replace that conserved quantity in the Hamiltonian. Good. So now, let P sub 1, which is a constant, we're just going to name it alpha. Alpha is a constant parameter in the Hamiltonian. So then what we have is H equals H of Q sub 2 to Q sub n, P sub 2 to P sub n T, and I'll just indicate that this alpha now is in there for bookkeeping purposes. Alpha is now a parameter. So now we have n-1 coordinates, n-1 momenta, and a parameter. Of course, it's a conserved quantity, but we've reduced the order of our system. And the canonical equations remain unchanged. And the reason we can do this is because all of these coordinates and momenta were essentially independent coordinates from the beginning. Okay. In other words, in Lagrangian mechanics, we have n independent coordinates, but the velocities are not independent of the coordinates or each other. But in Hamiltonian mechanics, all 2n of these, well, 2n-1 now, but originally 2n of these coordinates momenta were individual, independent coordinates, so to speak. And you can't do this with Lagrangian mechanics, so this is a definite advantage. There's a really important note here. In Lagrangian mechanics, you cannot substitute this conserved quantity back into the Lagrangian. What you have to do is, you can substitute it into the equations of motion and carry on. You can substitute it into the energy, which is what we did in the central force problem, which is essentially the Hamiltonian method, right? But we cannot substitute a constant value of a generalized velocity or generalized momentum back into the Lagrangian. Cannot. Substitute dl dq. So did I give it a letter? I'll just say k dot equals alpha back into L. Lagrangian. If you do, it'll look right, but it'll be wrong. And there's a great example for that I'm going to put on the homework. And that's this. So for the central force problem, L is, as we know very well, r dot squared, r squared, v dot squared, minus u of r. That's our Lagrangian, and we get Euler-Lagrange equations. So write out the Euler-Lagrange equations. Okay. This is homework, by the way. But I'll probably do most of it. Right out the Euler-Lagrange equation. Okay, so you do that. We find, of course, we've done this. We find dl d phi dot equals mr squared phi dot. We'll call lowercase l. That's our parameter. Okay, that's what I'm talking about. Alpha there. And you could be tempted to put this back into your Lagrangian. Now, going to do it, but I really should put a subscript of a skull and crossbones or something, because it's completely wrong. But we're just gonna call it L tilde. If I do plug it in, I end up with 1/2 M R dot squared plus L squared over 2M R squared minus U of R. Okay. Let's set this up. So this L tilde here, L tilde is it's an illegal Lagrangian. It's a false Lagrangian. It's a wrong Lagrangian. A forbidden, that's the wrong word. Is not a valid Lagrangian. So not valid. And the reason is that this piece of phi, which is what this is here, right, L, is not independent of R, okay? It's what it's done is it's mixed up the coordinates and the velocities. And what I want you to do is write out the Euler-Lagrange equation. For this thing, there's only one now because it's just R, right? R and R dot. So d dt dl tilde dr dot minus dl tilde dr equals 0. And show that it contradicts these equations up here. Okay. Just so this thing is all complete, show that you get a contradiction. You're not going to see that it's wrong just by looking at it. It's going to look like a regular equation. Show that it contradicts what you get up here, okay? Here you're gonna have two Euler-Lagrange equations, plug one into the other, you get a differential equation for R and R dot, and it will be different. This one, the true one, will be different than this illegal one, okay? So really important point, because the independence of the coordinates is so important in Lagrangian and Hamiltonian mechanics. The Euler-Lagrange equations were derived back at the beginning of the semester under the assumption that all of those coordinates in the Lagrangian were independent of each other, okay? And that's been violated when you mix them up this way, okay? So what's perfectly legitimate and very important here in the Hamiltonian method is not possible in the Lagrangian method. What you do is you write out your equations and just go to work with them, okay? But I'm just saying you can't recycle it back into the Lagrangian. So yeah, this is a good problem, an important problem. And so you guys will do that. Let's see here. Okay, great. So now we're ready to move on into a topic that where Hamiltonian mechanics really starts to be different than Lagrangian mechanics. Okay. Right now, in the sense of finding the solutions to the equations of motion, it's just an added technique, but there are actually some different properties of this whole scenario. And that's what we're going to talk about next. So we're talking about something called phase space. So phase space and the phase flow, we'll just say phase space. So now we have to go back to Lagrangian briefly. Lagrangian mechanics, right? L is equal to L of Q1 to Qn, so 1, Q1 dot to Qn dot. So the coordinates, their derivatives, nt. So generalized coordinates, generalized velocities, and time. Okay, so that's how we construct the Lagrangian like that. And we refer to configuration space configuration space is the space spanned by these n coordinates. So the space spanned by Q1 to Qn. So you could say the motion takes place in configuration space, and we have 2n second order differential equations. And so to solve them, we need 2n initial conditions. We need an initial position and initial velocity for each coordinate, basically. Okay. So that's what's going on in Lagrangian mechanics. We can contrast it to Hamiltonian mechanics. So in Hamiltonian mechanics, we have, and of course, Hamiltonian comes from Lagrangian, the way we've learned to construct it now. So Hamiltonian H is this function of the 2n essentially coordinates. We'll see later the coordinates and momenta can actually be interchanged. You know, their names, everything can just be interchanged on that. But there are 2n of these. Okay. We have 2n, and we have 2n first order differential equations. So what's called the phase space is the space of these 2n coordinates. So it's the space of Q and P. Let's see here. So it's the set of these Q1 to Qn to P1 to Pn tuples. And the motion of the system takes place in this 2n dimensional space. Phase space is 2n dimensional. Right, so it seems like the space is much more complicated, but the fact that you have first order differential equations makes things much more simple. So we'll put that up as a definition. Now, of course, for illustration purposes, all we've got is n equals 1. Okay. Because then 2n is 2-dimensional, and we can draw it on the board here. But the n equals 1-dimensional example does quite a bit for us. Like the n equals 1-dimensional example, make everything clear. So one thing I can of course do is just draw a vector, label both of these with vectors, and there's my mock-up of a 2n dimensional space, right? But of course we're gonna use n equals 1 and actually draw this. So example, or comma, n equals 1, and then we have Q and P. So for a one-dimensional system, the motion takes place in this space of Q and P. I'm gonna wanna go with the big picture. You have both of these. I'm gonna go ahead and I'm gonna draw a decent size n equals 1 graph here so we can see everything. Okay. So yeah, this is the phase space for n equals 1, Q and P. And see, any point in phase space, what does a point in phase space mean now? So, a point question mark. Well, let's just do our example and get this illustrated. We're going to use the harmonic oscillator. Simple harmonic oscillator. Now, this is something we can get behind, right? L is equal to 1/2 mx dot squared plus, I'm not even going to write u of x, but plus 1/2 kx squared, and h is equal to p squared over 2m plus 1/2 kx squared. So far, something we probably, hopefully, feel pretty comfortable with, harmonic oscillator. Now, what about the canonical equations? We have Q dot. Here's what we're in the, you know what, we're gonna call this Q here as well. That works, okay. Now Q dot is equal to dH dP, and P dot is equal to dH dQ. Gets the minus sign in front of it. So yeah, we're going to be concrete with this. So Q dot is equal to P over M. P dot is equal to minus K times Q. Okay. So what about this QP right here? This is a point in phase space. I just drew a point in phase space. Q dot P dot can be thought of as a vector. Okay, I'll do that right under here. Q dot P dot is a vector in that phase space because, first of all, it has its definition, dH dP minus dH dQ. Right? This is a vector, and this is a vector as a function of Q and P. Okay? So Q dot P dot is a vector function of Q and P, and it really just gives the direction. So it's just a vector, it gives the direction that our system would move in. Okay. And since I know where this one is going, I'm going to relabel here. We're going to be going somewhere like this. Okay. Because QP can now be thought of as a position in phase space, and its time derivative is a velocity in phase space. Okay. And therefore, its time derivative is tangent to the phase curve. The time derivative is tangent to the curve that Q of P, T of P would take. Okay. So let's do this one thing at a time. We'll send this up here. Yeah, okay, that's all good, that's good. Yeah. Is that board going? That's as good as it gets. Yeah. So let's continue this. So here we have Q dot P dot. So d dt of this vector QP, right? And what do we get here? We have P over M. P over M. These are Hamilton's equations, and minus KQ. So what we have here is Hamilton's equations, and the right side of Hamilton's equations generate a vector field in phase space. This is a vector, so it's generating a vector field in phase space. Vector field in the phase space. And since that's the time derivative of this vector, that gives on the direction that that vector is pointing. So, yeah, so Hamilton's equations, I'll put that as a note. Hamilton's equations generate a vector field. Phase space. And what we're going to do, we're taking the harmonic oscillator, and to make it really simple, we're going to let M be equal to 1 and K be equal to 1. Okay, so we won't have any problems there. So the harmonic oscillator, for the purposes of drawing our picture, okay, harmonic oscillator I was going to use that one, but here we are down here. Okay, we've got Q, P, we have H is equal to P squared over 2M plus 1/2 K Q squared. When I say M and K equal to 1, just for the purposes of making our drawing, because this P over M minus KQ, let's just start here, okay. So what vector do we have when Q is equal to 0 and we're up there at positive P? Okay, this will be a 0, this will be a 1, okay? So Q dot, no, so we'll have Q dot over P dot, that direction vector is just going to be P over 0. So since P is positive, that vector is pointing here. Now let's go out to this point, okay, along the 45-degree angle. Then Q dot and P dot vector will be the vector P minus Q. Okay. P is positive, Q is positive minus Q, so we're going to go like this, okay? And when we're here, the roles get changed, it goes like that. When you're here, it goes like that. So what you get is a circulating thing, and as you go away from the origin, the vectors grow in length. So if you're closer to the origin, they're going to be shorter. Okay. draw. You draw a lot, what you're getting is a circulating vector field. And if you draw a whole lot of arrows, in fact, you guys could probably program something, mathematic or something, to draw a bunch of little arrows for you. You'd get this circulating field, and it would, the phase curves would look like this. And there's one thing we can say even about these phase curves. Remember, harmonic oscillator, H is constant. So we can get the phase curves, in this case, very nicely. We would have P squared over 2MH plus Q squared over 2H, and I'm going to divide the K down here, would be equal to 1, right? I just divide the whole equation by H, and I would get this. And we've been doing ellipses recently enough, so we would recognize that as an ellipse. We could have P squared over 2M, I'll go ahead and call HE, take the square root of that and square it, plus Q squared over 2E over K square root squared equals 1. Right, these would be the equations, these would be the, this is the equation of an ellipse. Phase curves would be ellipses. Phase curves are ellipses, which is what all these little arrows showed us. Okay, working our way left on the board. What about the actual solutions? Okay, we know the solution to the harmonic oscillator. The solution, we would say Q is equal to, I'll use the letter A, cos omega t plus some phi, and P is M times Q dot, so let's go ahead and write that. M Q dot equals M. It's going to have a minus omega A sine omega t plus phi. So that's QP. QP is a vector. And these solutions are, of course, of a dot going clockwise. Okay, clockwise around here. Make sure you see that. Okay. When you're doing X and Y and your cosine and your harmonic oscillator or your circular motion, then you've got the plus sign in front here. Okay, the minus sign means instead of going clockwise, it's going counterclockwise. So, I'm sorry, the other way around. Instead of going counterclockwise, it's going clockwise. So that's a clockwise motion. Okay. And these are the basic features here. Okay. So the motion, this generalizes as follows. Let me set that up. So now we can summarize the motion of the system is the motion of a point in phase space. And this was only possible because we had the first order differential equations. That's why you can take that point and draw an arrow right next to it, because of the first order equation. And because you generate a vector field here, the Hamilton's equations generate this vector field, okay? And a vector field in this phase space can just be analyzed in terms of geometry. What I've shown you here is the geometry of a circulating field. Okay, so I want to summarize these points. So, summarizing. First of all, we have, so summary for H equals H of, I'll just write vector Q, P, and T. So phase space is the set of these Q, P. You could call these vectors, right, 2n dimensional. And then we have a point in phase space can be considered, an arbitrary point in the motion, a point in phase space can also be considered an arbitrary point in phase space is an initial condition. So Q naught, P naught is an initial condition and Hamilton's equations tell us what happens to that initial condition. You have one right up here at the top, it circulates around. Okay. If you have one here in the middle, the line that bisects the first quadrant, it also circulates around. Okay, they're all circulating clockwise there. Q, this is initial condition of our system. So this is a point in phase space, a phase point. Hamilton's equations generate a vector field on the phase space. And that vector field shows you essentially the trajectory of your point in that phase space. Now, we can actually visualize it for n equals 1, but mathematically it's holding true for any finite dimension n. So generate a vector field in phase space. And finally, the motion of the system is the motion of that point in phase space. Equivalent motion of the point suppose you have a system with some large number, n degrees of freedom, then you still have a point in this 2n dimensional space that is moving around in that space. Okay, so it's a point that's moving in a large space. Okay, let's check. All right. Yeah, that's probably as far as we'll do for today. Let's see what else we could, in terms of this. Yeah, you really want to take a close look at this harmonic oscillator because everything is there. The generation, the phase of the vector field, what it means. So once again, we've got our harmonic oscillator here. We've got this point in phase space right here. Right? It's telling us at a certain position in momentum of the system. So we could take that as an initial condition. Yeah, it's going to go in that direction next. Okay. And if you make the vector field, draw it fine enough, you see a flow there. The expression phase flow. I will add a little more terminology. We've got this set of phase points space. We could outline a little collection of points like that. Okay. Yeah, and what are they going to do? They're all going to follow this type of trajectory here. Interesting theorem that goes with that, but I'm not going to introduce that now. Yeah, let's just do this terminology here. We've got the phase fluid is all of this phase space. You can think of it as a fluid, and the Hamilton's equations generate this flow. Okay, so we've got the phase fluid, and we've got the expression the phase flow. For the moment, we're going to leave it at that. We'll define that a little bit more next time, and we'll get some really nice examples to illustrate this. One step beyond the simple harmonic oscillator can be very interesting to see as well. But yeah, the idea is, and this is used in statistical mechanics a lot, that you've got this phase fluid and what these initial conditions can do. In this case, for a simple harmonic oscillator, of course, they go around and return from where they came from. Okay. So good. That's some terminology that we'll continue with next time. Until then, let's see. Well, we had a couple homework problems, so we'll leave it at that. Good. See you next time.